Okay, so let's take a break from the more data analysis side of astronomy, and let's look more at how we do astronomy and how we collect the data that we need to do astronomy. So this is a project that I've been working on since June of this year with my supervisor, Xiaoji Chen, and we're essentially building a prototype device that could hopefully revolutionize multi-object spectrography. And as far as I know, we are one of the only 3 groups in the world looking at this technology, which is pretty cool. All right, so let's start off by actually talking about what spectroscopy is. It is a powerful technique in astronomy that allows us to find out things like what objects in the universe are made of, what concentrations of chemicals they have, and sometimes also things like their velocities and temperatures. And the way that single object spectroscopy is done is you have your field of view, you have the target star that you care about, you have some sort of plate or something that's blocking off all of the light except the light from the target that you want. It falls on a grating or a prism or something that turns that light into a spectra, and you detect that with a detector. A multi-object spectrogram is really similar, but as you might expect, instead of a single slit, it has multiple slits and is able to do spectroscopy for multiple objects simultaneously. However, the current technology is often really complicated, is really expensive to build, has a lot of moving parts and pieces that just take forever to get right calibration wise. And astronomers often need to plan out their targets and make their slits well in advance before they actually get to do the observation. Here, I'm about to show you a clip that has been sped up from the Miradas multi-object spectrograph in La Palma, Spain. This was taken by my supervisor, who actually worked on this in grad school. So as you can imagine, these big mechanical arms, super expensive to make. You cannot just buy them. You have to design them yourself. And they're like, just look at all the wires and moving components. That's crazy. So now you can't really send something like that to space, and you can't really put something like that on any telescope you want. But what if there was something that you could buy that already exists and turn it into something that essentially does the same thing that this crazy device does? Something that you could send to space, or something that is small and light enough to be able to send to space and doesn't cost nearly as much as the JWST's micro shutter array costs. So you don't spend billions of dollars. Well, meet my friend, the DMD, or digital micromirror device. What this is a grid of microscopic mirrors that you can turn around to point in either plus 12 degrees or minus 12 degrees. And this is great because you can redirect light to wherever you want to send it. Let's take a closer look at at what these mirrors look like. Found a video yesterday that described them as micro Cheez-Its, which is great. And it's surprisingly accurate because they have this tiny hole in the center of them, which is how they connect to the electronics underneath. And that basically turns them in one direction or the other. And you'll notice they're only 10 microns in side length, so crazy small. And now let's look at the DMD I'm working with in action. So this is just really tiny mirrors moving really, really fast to show us Kirby jumping around. And this is, I think, the first thing that I made when I got my hands on this thing. I sent it to my supervisor. She was like, this is crazy. So how do we turn this little thing into a multi-object spectrograph? Well, so this is the concept design. You have your target field, it comes in here. You make all the mirrors point to an imaging channel, which takes a photo of your field. And then you pick out all of your targets on that field. and program it so that the mirrors that the light from those targets is landing on turn to then go to the spectral channel and give you your spectra. And this is what that device looks like in my lab. So here's your imaging channel, here's your spectral channel, here's your DMD. And this thing is just slightly bigger than how big the actual instrument is. So compare this to the huge arm thingy that I showed you earlier. And it does the exact same thing. So now I'll talk about some of the results of my alignment, because that's what I'm working on first, kind of aligning all of the optical components before we can actually get data and science done. So in this image, each dot you see is a grid of 3x3 mirrors that have been actuated to point towards the imaging channel. And they give a full width half max. So the full width half max of each peak is about 3.2 pixels, where each pixel is about 6 microns in length. So, we are already able to resolve it pretty well. And this was just a rough alignment. Last week, I was able to align it really precisely and see this grid of dots where each dot is just a single mirror. So we're basically close to resolving 10 microns, which is super fun, but we're not done yet. Moving on to the spectral channel, this is still a very rough alignment. What this photo shows is I have programmed 10 randomly distributed slits that pointed to the spectral channel and just shown light through like a mercury neon lamp on it. And of those 10 slits, we see 9 spectra with just a rough alignment. And this is one of those spectra zoomed in. So here you can see the cleaned up raw data. And here you can see that we're getting a pretty good signal to noise ratio already. So yeah, multi-spectra resolving capabilities are already possible, and we're not even precisely aligned yet. So yeah, in conclusion, multi-object spectrographs allow for simultaneous spectral observations of multiple targets, and the DMD-MOS is a mechanically simple, efficient, and cost-effective alternative to the current technology that exists. It has separate imaging and spectral channels, so you don't lose any of your light at all. Because with something like the JWST, when you're using microshutter arrays, all of the light that you're not sending to the spectrum, the spectral channel, you're losing. And we don't want to do that. And the way that the DMD-MOS works is it uses microscopic Cheez-Its to act like slits instead of actual physical slits. And that directs the light from the target objects to the spectral channel. And our preliminary results are already very promising. So the future work that I still need to do over the coming 6 months is more precise alignment of both channels, especially the spectral channel, figuring out what pixel on the imaging channel corresponds to what mirror on the DMD, so that if I were to pick out stars on the imaging channel, it would turn the right mirrors on the DMD. Calculating the wavelength solution at different positions. What this basically means is if I have multiple spectra all over my spectral channel, I know which line corresponds to which wavelength. And finally, hopefully, getting this thing on the telescope at the Carr Observatory and collecting some real data.